All right, the next topic I want to talk about in this class are what are called integration tables. And we're actually still in section 3.5. So when you think of 3.5, you might be thinking of integration by parts. That's what we learned in 3.5. But your book actually combines two different topics in 3.5. First, it talks about integration by parts, which we did as the last topic, and then it talks about these integration tables. And I feel like that's a lot of information. I feel like integration by parts itself is pretty major, and integration tables are not nothing for sure. So I kind of wanted to break them into two different topics for our class. So technically, we're still in 3.5, but we're no longer talking about integration by parts. We're now talking about integration tables. So what are integration tables? To understand integration tables, I think it helps to have like a big picture overview of calculus. So your basic Calc 1 class, chapter 2 in our class, what you learn is how to take derivatives. So the basic idea is I can write whatever function that I want, right? I can just kind of start throwing some stuff together. Doesn't really matter what I do. Sure, that seems sufficiently complicated. And then I can ask you to take the derivative of that function. And the nice thing from a teaching perspective about Calculus 1, Chapter 2 in our book, is I don't have to think too carefully when I make these problems. I can kind of do whatever I want to do. And the reason why is I'm guaranteed that there'll be an answer. No matter how messy I make this thing in here, it's possible for a student to find the derivative of that function. And that's for a fact that I haven't yet mentioned in this class, but it's kind of an interesting fact. And the idea is every single function has a derivative. A little bit more technically, every elementary function has as its derivative another elementary function. But when I say it that way, you're like, well, what's an elementary function? And basically, what an elementary function is just a function from your perspective. Anything that you've ever seen as a function is technically what's called an elementary function. An elementary function is a function that you can come up with a finite amount of multiplication and division and exponents and logs and all the different things that we've seen that make up a function. Technically, you can have a function that's not an elementary function, but you wouldn't be able to write its equation with our standard notation. So it's not even something that we're considering in our class. In our class, a function is an elementary function, and a nice property of derivatives is that every elementary function has as its derivative an elementary function, which is really cool, and something that's easy to take for granted until you get to Calculus 2. And Calculus 2, in other words, chapter 3 in our class, is where you calculate integrals. You get antiderivatives. And there's a big problem with me asking you questions in calculating integrals. And it's I have to be really careful in terms of how I ask them because not every function has an antiderivative. Every function has a derivative, not every function has an antiderivative. And again, I'm speaking a little bit loosely here. I should be using the phrase elementary function instead of function, but anyone who's watching this video, from your perspective, they're the exact same thing. The point that I'm trying to make down here is I can't just go randomly throwing symbols together and ask you to find the antiderivative, because there's a chance that antiderivative can't even be written as a function. And even if that's not the case, there's a decent chance that it's not at all reasonable to come up with the antiderivative. Antiderivatives, loosely speaking, are a lot harder than derivatives. Calc 2 teachers have to be a lot more careful than Calc 1 teachers in the questions that they ask because they might accidentally either make a problem way too hard for even the most advanced Calc 2 student or even ask a question that doesn't even have an answer. For example, an integral that looks as innocent as the square root of 1 minus x to the fourth power dx is actually impossible to figure out. You can try whatever methods you want, use substitutions, integration by parts, methods we haven't even learned in our class, and you won't get anywhere. Which is kind of surprising as this doesn't look all that hard. Another classic example of something that cannot be answered is 1 divided by the natural log of x. If you're trying to figure out the antiderivative of that, don't bother wasting your time. You're not going to get anywhere. The way I like to think about it is the rules that we have for Calculus 1 are kind of more powerful. They allow us to tackle any function that we want. But the rules that we have in Calculus 2, they're kind of limited. I mean, really at this point in the class, all we have are u substitutions and integration by parts. And those are the only two rules we're gonna get. There's really only two major rules in a Calculus 2 class. There's a few more identities that some classes get into that we're not going to. And if you're wondering, the reason we're not going to get into these identities is because we're avoiding trig functions in our class. So things like sine and cosine and tangent, if you've seen those in another class, because trig isn't a prerequisite for our business calculus class. All that to say, we're essentially done with rules in our class, meaning we essentially know how to integrate everything that we're going to learn how to integrate. But there is one little caveat, and that caveat is, if you look in the back of the book, there's some tables. And you're like, wait, the back of what book? the back of any book. Any calculus book, in the back of it is going to list a whole bunch of integration tables because, generally speaking, figuring out integrals is really hard, and even after a student becomes an expert with all the different rules, there's still a lot of functions they won't be able to figure out the antiderivative of. So books kind of cheat. They list these huge tables with tons of different formulas, and the student can just use those different tables. What I'm going to do in this section is teach you how to use those different tables. Couple comments before we get into the tables. First of all, as I mentioned, they're in every single book, although they look a little bit different in every single book. But basically they follow the same different structure. They're broken up into different sections. In our book there's 10 different sections. And the idea is there's going to be like 100 or so formulas, so it'd be impossible to keep them all straight if they weren't broken up into different sections. The second comment that I want to make is you could argue, do I really need to learn all this stuff, integration tables? Like, I won't be able to use them unless I can look in the back of the book. And if I have access to a book, don't I have access to like Google? Couldn't I just use some sort of solver online to figure out the answer instead of figuring out a table that I can use to get the answer? And frankly, the answer is yes. In this age of technology, you could argue that integration tables aren't really necessary. However, I'm still going to teach them because 2 reasons. I'm supposed to teach them, and secondly, it's not as straightforward as just looking something up and getting your answer. Using the integration tables involves a fair amount of skill. Typically, they involve different u substitutions, and you have to be a little bit clever in terms of how you use them. So it's definitely not nothing. At a minimum, they refine the skills that we've already built up with u substitution and integration by parts. So I think it really is good to learn this section, not just because I'm supposed to teach it. Anyways, I mentioned there's these integration tables, and I mentioned they're broken up into 10 different sections in your book. The first section just includes basic integrals. So these would be things like the power rule, or the fact that the antiderivative of e to the x is e to the x, things like that. Things that we learned long ago that we'd never reference the back of the book to use. So for our purposes, we can completely ignore section 1. Section 2 deals with trig integrals, and as I mentioned before, we're completely skipping anything trig in this class, so this talks about sines and cosines and powers of those functions. But since you don't even need to know that those functions exist, we're going to completely skip section 2 also. That takes us to section 3. The first section that will actually be useful for us. Although, as you see that I wrote right here, it's not really necessary. Because although section 3 gives you a bunch of different identities here, it doesn't really give us anything we don't already know with u substitutions and integration by parts. So let me show you how they work. Generally, the variable that's used in here is the letter u. And when you see other letters involved, they typically represent constant. So when you're looking through these tables, when you see a, just think it's a constant, any number. And if there's 2 different constants in a given problem, maybe they'll use a's and b's. When you see n's, typically in math, n is meant to signify a positive whole number, so like 2 or 3 or 4, and if there's more than one in a given problem, they might use n's and m's. And then instead of using the letter x as the variable, they use u's as the variable, because typically what happens when you're using these tables is you have to do a u substitution to get your problem into the form that fits what you see in the back of the book. So when you see u, think variable. So let's take a look at what 42 is really telling us. For 42, think. You're being asked a question like, what's the integral of x e to the 2x, for example? The point that I want to make about this question is, as I talk about up here, you already know how to figure out this. This is a question you've seen before, right? We could do this with integration by parts. We would let u be equal to x, and dv would be equal to e to the 2x dx, in which case du would be equal to 1 dx, and v would be equal to 1/2 e to the 2x. And when we throw all the different pieces together, we get that this integral is equal to u times v, so 1/2 x e to the 2x, minus the integral of v du, so 1/2 e to the 2x times 1 dx. This part over on this side is done, 1/2 x e to the 2x. Over on this side, we can take the 1/2 and pull it out in front. And what's left is to figure out the antiderivative of e to the 2x power. And the nice thing about e to the 2x power is that's an antiderivative that you can figure out. In fact, we've already done it up here when we said dv was e to the 2x and we had to figure out v. The antiderivative is 1/2 e to the 2x plus c. So when I simplify things a little bit, I get 1/2 x e to the 2x minus 1/4 e to the 2x power plus c. And you're like, oh, okay, but where do we use the tables? We didn't use the tables at all. We didn't need to. My point is that table 42 isn't really necessary as long as you're good using integration by parts. But if you really didn't like integration by parts, or if you thought that was a little bit too much work to do, what you could have done instead is come here to our original question, done a u substitution, where we're going to let u be equal to x, in which case du is equal to 2x, and then note that playing the role of the a is equal to a 2. With these three assumptions, this formula 42 right here tells us that the integral of, instead of writing u, I'm going to write x, e to the, instead of writing a times u, I'm going to write 2 times x, and then instead of writing du, I'm going to write dx. It tells us that this, which is exactly the question that was asked, is equal to 1 over a squared. Remember, a is equal to 2, so this is 1 over 2 squared, in other words, 1/4, times a times u, so 2 times x, minus 1, e to the au, e to the 2x, plus c. What 42 is doing here is saying if you don't want to use integration by parts, just plug in all the different numbers and this is the answer. And you might be like, wait a minute, that's the answer? That's not what it looks like down here. Well, I think they're equivalent. If we take the 1/4 and the e to the 2x and distribute them into the parentheses, 1/4 times 2x minus 1 is 2/4 x, in other words, 1/2 x, minus 1/4. And then I still have this e to the 2x. And maybe now you can stare at red and stare at purple and convince yourself that they're equivalent if we just took the e to the 2x and distributed them through the parentheses. The point that I'm trying to make is, these are equations that tell you the value of different integrals. In this specific case, section 3, all of these different integrals are things you could already figure out, with the exception of 44 and 45, because we haven't looked at trig functions. But if we did look at trig functions, you would have been able to figure out 44 and 45. 42 is really just integration by parts. In fact, 43 is also just integration by parts. The only difference here is instead of starting out with x, e to the 2x, we could start out with like x squared, for example, e to the 2x. And maybe you recall, we've seen that problem, x squared e to the 2x, that what we have to do is the integration by parts formula twice. You do it once and it kind of simplifies down to something that looks like this, and then you do it again. 43 is just giving you a shortcut for exactly that. 46 is also something that we can do using integration by parts. This is what I described as a tricky application of integration by parts. You'd use it on questions like the integral of the natural log of x dx. This was the application of integration by parts that didn't seem like an application of integration by parts because it's not something times something. But we saw this little trick. We were going to let u be equal to the natural log of x, and then dv was just dx. And when we plugged in all these pieces, this simplified, and we were able to figure out what the antiderivative natural log of x is. It's equal to x times the natural log of x minus x plus c. Maybe you remember that example from the previous section. At any rate, 46 is just telling you that exact same example. Turns out 47 is also an example of integration by parts. In fact, it's an example of integration by parts that I gave you. I think we had something like x to the 3rd power natural log of x or something. I don't remember what the numbers were. But when you used integration by parts, you were able to figure out the antiderivative. 47 is just a shortcut for that. And then finally, 48, this is just a u substitution. It says that if you're ever in the instance where you're taking the integral of 1 over u natural log of u. So for example, if I ask you the question, what's the antiderivative of 1 over x natural log of x? One way you could solve this problem is with a u substitution. You could let u be equal to the natural log of x. If u is equal to the natural log of x, then du is 1 over x dx. So that allows me to rewrite this integral as the integral of 1 divided by u du. Make sure you can see how all these pieces change into these pieces. This is an antiderivative I'm comfortable with, right? This is just the natural log of the absolute value of u plus c. But this isn't my answer because u is a substitution that I did. I got to plug that back in and I get the natural log of the absolute value of whatever u was equal to here. Natural log of x in this case. Without using this table at all, I can figure out that the antiderivative of 1 over x natural log of x is just equal to the natural log of the absolute value of natural log of x plus c. All I have to do is this little u substitution. But again, if you didn't want to use that u substitution, what you could do is use the tables. If you're using the tables, it would be a little bit different. Now what's going on for u is it's just equal to x, because my goal is to change this equation into what I see up here on the left side of the equation. U is x, du is dx. That allows me to change what I have written right here into the left side of this equation. So all I have to do is copy the right side of this equation, changing all my u's into x's. I get the natural log of the absolute value of the natural log of x plus c, the exact same answer that I got down here, without doing this clever u substitution, instead just substituting to use these tables. Anyways, the point of all this talk is section 3 is not really necessary, but it can save you some time. Every question that you'd use section 3 for, you could already answer with the knowledge of our class, but you might prefer not to. So let me show you an example where we're not going to. Here's a problem. We're evaluating the integral of x times the natural log of x squared plus 1 dx. It's not obvious at all, but if we do a substitution where we let u be equal to x squared plus 1, then du would be equal to 2x dx, and therefore half of du would be equal to x dx. With this substitution, this integral becomes the integral of, instead of the natural log of x squared plus 1, I could write the natural log of u. And then instead of x dx, I could write 1/2 du. I got a constant that I could pull out in front of the integral, so I get 1/2 times the integral of the natural log of u du. At this point, I could figure out the antiderivative of the natural log of u du doing integration by parts if I really wanted to, or I could come up here to equation 46 and be like the integral of natural log of u du is just equal to u natural log of u minus u plus c. So instead of writing the integral of natural log of u, I'll write u natural log of u minus u plus c. I don't have any integral symbols down here, so I don't have any more calculus to do. All I have to do is change all my u's back to what they were equal to, x squared plus 1. My final answer would be 1/2 times x squared plus 1 times the natural log of x squared plus 1 minus x squared plus 1 plus c. You could rewrite this if you felt like it, getting rid of various parentheses and such, but really I don't even want to. I want to call this good as my final answer and just make the point that by using the tables from this line to this line, I cut out integration by parts, which made my work a little bit easier to do. Using these tables weren't obvious, right? When you first were given this problem, it probably wasn't obvious that we were going to end up using table 46 to solve it. Often you have to do a u substitution, and sometimes that u substitution isn't obvious to get it to fit the left-hand side of one of these equations. That's why all these equations are written with u's as the variable instead of x's, because we assume that the student is going to have to do some sort of substitution. Sometimes it's a really easy substitution where u is just equal to x, and sometimes it's a more involved substitution where u is equal to x squared plus 1, for example, and have to make sure that du works out all right. I think about the tables as an application of our knowledge of u substitutions. It's definitely not as trivial as just copying a formula down, because often there's work that has to be done just to use the formula in the first place. Because it's not trivial, I want to show you a lot more examples, but I think we've done enough for this first intro video. In the next video, I'll just do a bunch of examples with other sections, because I mentioned there's 10 of them, and we've really only seen one of them because we skipped section 1 and 2, so 3 was really the first section that we've seen.